All right, so clear up some things from earlier this week. There was, okay. You guys remember the last lab you did? Now, the next week I do have another lab lined up with you guys. It's going to be related to projectile motion. But the first lab you guys did, you guys remember, so car and ramp lab, you were rolling the cars down the inclines. Half of you guys were looking at distance as a function of time. And then remember we did that axis manipulation? We were saying, how far did the car go? Well, I know it was centimeters, but it's going to use our conventional unit meter. As a function of not time, but how do we manipulate this bottom axis? We did what? It wasn't time, it was time squared. You guys remember that? Time squared? That kind of abstract idea. But interestingly enough, all the points pretty well lined up on a straight line. It was, plus or minus a little bit. It was something like that. So you guys go like, zip, just do like a line best fit like that. You guys remember that? Okay. And I think I mentioned that the slope of this line was, well, let's look at the units of this. Right? Because I talked a little bit about this, but I realized I didn't actually go all the way and tell you guys fully the story of this. Guys, what are the units of the slope of this line? What's the rise over run? That per that. Yeah, guys see it's an acceleration unit? It's like meters per second squared. It's meters per second squared. You guys see that? Right. So the slope has some units in meters per second squared, right? Which looks like acceleration. So does the slope of that line represent the acceleration of the car? The answer is not exactly. And the reason I'm for sure doubling down on this point is because this is totally a question that AP could ask. I've seen AP ask this kind of question before. Okay. Let's look at your distance versus time equation for something starting from rest. Doesn't it go like this? X equals 1/2 AT squared, right? Isn't that the equation for how far something moved as a function of time? Hey, isn't this the Paul Hewitt mineshaft equation? College. This is the college equation, isn't it? Is that? Now, how does that compare to this graph? Right? Well, doesn't this graph look kind of like y equals mx, something like that? Okay. Like plop in the equivalent parts. Okay, so x, how far it goes, is equal to, maybe I'll just call it slope. I'll just call it slope. Just make it super obvious. I mean, obviously this is the slope, right? So I'll say slope times t squared. T squared is like your x value, right? Well, in terms of like just pure algebra. Right? That takes the form y equals mx. Right? All right. So if you didn't see it before, I bet you see it now. Guess how this line look pretty much the same? X equals something times t squared. Right? Now you see it. The slope of this line doesn't exactly represent acceleration. It represents what? Half the acceleration of the car. Yeah. And again, I've seen AP ask questions like that all the time. So there you go there. Okay. So acceleration, or the slope of an x versus t squared curve represents half of the acceleration of whatever's moving. Okay. You guys got that? Okay. All right. Then there's another problem that I wanted to go over with you guys. I fit it in at like the end of one day. It was like the last 5 minutes. And let me see if I can find it on. It was what's this one right here? It was number 20 from your college textbook problems. They gave you an acceleration versus time graph. You see that? Acceleration versus time. Right? And well, there were some questions, and I did most of it with you, but not as much as I wanted to. Right? So let me make up my own that's really similar looking to that. It says, you guys know I'm about finished putting your quiz together, right? The quiz I'm going to get you guys by the end of next week. Okay. And why am I bringing that up now? Wonder if it has something to do with what I'm going over right now. It's a good chance. Okay. So let's make the standard 3 graphs like we've been doing. Right. Now the A versus T do a sideways T graph, but the other ones can just be first quadrant graphs, just for the particular example I'm going to do. Okay. So we're going how far in meters, how fast in meters per second, and what's the acceleration meters per second squared. Each is a function of some time taken along in seconds. Okay. Okay, so that looks pretty standard. That could be anything, like any story could fit into those graphs. Okay, so what story are we going to be looking at? Okay. So let me just make up some random acceleration versus time graph. I'll make one. Let me go just real straightforward here. What if there was something like this? And then I know there's some jumps there, but maybe there's like a really steep change, something like that. So it basically steps down like a staircase, and then maybe at the end of this interval it just goes back to 0 and then just stops there, something like that. Okay. So what if you had a curve that looked like that? Okay. Now, any particular scenario, I usually tell you what the scenario is first, and I say, can construct the graphs based on that particular motion. Okay. And I usually start with the V versus T graph and then branch out from there. That's how we've been doing this over and over. Okay. Now, here we're approaching from a different point of view. I mean, I haven't given you a story yet. I just created some graph, out of some abstraction. And, also I gave you the acceleration one, E. Now, do you think, if you know the acceleration, you could actually figure out the V versus T and X versus T? Bet you could. Now, actually, you would need a little bit of additional info. You'd have to know the starting speed. Let's suppose I tell you it starts from rest, so at time 0, it's speed 0. Okay. And looking at X versus T, let's say it also starts at position 0, at time 0. Okay. Technically, you'd have to be given that. Sometimes it's implied if there's like the word drop or something. Right? Anyway, okay, so I'll give you those points anyway. Okay. Can you guys create a V versus T graph based on what I just drew for A versus T? See if you can do it. Because if you can do this, then you're that much readier for this particular quiz question that might be coming up. And also, you should feel confident that you should know the relationships between these graphs for physics. See if you can do V versus T before I show you what it looks like. Create V versus T. Kind of glance around the room. I wonder if anybody's going to get this. I hope so. Hey guys, what property of an acceleration versus time graph tells you velocity versus time? What property? Something to do with the area under the curve, right? Something to do with that. And then if you want to check the work backwards, then V versus T, something about the slope tells you acceleration. Trying to go back and forth. Let's see if you do that, and you'll be able to solve it both ways. Yep, Camden got it. Okay, got one winner. Lucas got it. Got 2 winners so far.
Oh, sorry. Sorry.
Who else is going to get this? Oh yeah, Sam got it. Okay. Well, that's at least 3. And you know what? I'm sure I passed up a couple of guys that maybe got it right as I passed you. So got at least 3 winners. These 3 guys I'm gonna put together. Okay. All right, so start from rest, just to have a point to start. Okay. Hey, if you're accelerating this is constant acceleration, isn't it? In fact, if you pay real close attention, all the acceleration graphs we've ever done have been some constant values. There's like flat lines like this. Okay. And haven't all the V versus T graphs been, well, for the most part, like some version of straight lines, right? So maybe we should break this up into looks like 3 seconds or 3 equal time intervals. Is this going to start out going like that, like speeding up? Okay. So if you press on the gas pedal in a car, maybe I haven't given you guys a story yet, but maybe you're in a car, right? You're pressing on the gas pedal and you're accelerating at a constant rate. Doesn't that mean you're picking up speed at a constant rate? Right? And doesn't the slope of this curve here represent this coordinate? Right? All right. How about during the next second? If there's like 1, 2, 3 seconds, right? What's this part of the curve look like? Yep, flat line. Because if there's, hold on a minute. If there's 0 acceleration, does that mean the car is parked? Not necessarily. In this case, no. It just means the car is not doing what? Yeah. right, not accelerating, not getting faster, not getting slower. It's just not changing what it's doing, right? It's in motion, and it's just not going to change that. Right? Or if you want to go the other way, from V back to A, you say the slope of that constant velocity means zero acceleration, means the coordinate on A versus B is zero at that point, right? So fair? Right. How about the last second? What's going on? This car is doing what? Yeah, hitting the brakes, slow down. It has negative acceleration, right? Like that. So it's accelerating just in the negative direction, therefore it slows down. Oh, notice what I did here, and then again, I'll walk around the room so some of you guys got this exactly right. See how I have the final velocity is back to zero? It looks like this car came to a complete stop. Right? How did I know that was going to happen? How did I know it wasn't going to be, I don't know, in any other point? How did I know it was going to exactly come to a stop? Oh, yeah.
He was braking for the same amount of time he was accelerating for.
Exactly. Yeah, you guys hear Warner? He's saying he's braking for the exact same time that he was speeding up for, right? And also the same magnitude of acceleration. Basically, this rectangle here, whatever that area is, this negative rectangle has the same area, just negative. Right? So they cancel out. Right? That means he was acquiring velocity during the first second. He was losing velocity the third second, and it was exactly washed out. So his net change of velocity was zero. And then, yep, from beginning to end, his net change of velocity was definitely zero. Right? How about displacement? We haven't even talked about displacement yet. But let's go do that. This is 2 steps removed from acceleration. Okay. Or if you're taking calculus, I don't know if you guys know this yet. I'll see. The process we're doing, there's a calculus process that starts with an I. It's called what? Oh, you're not there yet?
Yeah.
Okay. Okay. All right. So if you're doing derivatives, so it's like x to v and v to a. Right. Eventually, you're going to do a process called integration, and that's going a to v and v to x. Okay. So good, you guys sort of head start there. Now this one's the trickiest one to put together. Well, give you guys a minute. Do the same thing. I want to walk around the room and see how many guys get this one. This one's real tricky. Well, I don't know. Maybe if you've internalized and digested everything you've learned in class so far, then you can definitely piece this together.
His velocity never reached negative, so he was always going forward. He just slowed down.
There, x versus t curves, they tend to take what shapes? Yeah, parabolas. Give you guys a hint. Okay, so there's some versions of parabolas involve some little pieces of parabolas. But you know what else? See that second for the v versus t curve, how it's like just flat, like zero during the zero acceleration segment. At zero acceleration, that means your velocity is constant. Yeah, and x versus t, it'd be like some straight part, like a linear type relationship. Okay, so yeah, you're gonna have some pieces that are parabola shaped. You're gonna have maybe the segment that's like a linear type shape. Who's gonna get the? Oh, Warner got it. All right, Warner, winner. Looks like Lucas got it. Good. I think I'll call that a win. Right, so Dean got it.
Hi. You have a staircase, a
We're
trapezoid,
just gonna get
and
the.
then that.
Looks like Kaylee figured it out too. All right, so I'm getting a few winners. I'm sure some of you guys got it probably after it passed me. So, do you guys remember, hey, if you drop a ball from rest, doesn't it just look like the first second for each of these graphs? And that would just be a parabola shape that does something kind of like, I shouldn't have made it so steep. There's something else I want to do right here. Make this a little bold. Say it does something like that during the first second. Okay? Then, during the next second, right, it's just constant velocity. Now, constant velocity, in terms of equations, doesn't it just turn into x equals vt, like distance equals speed times time, sort of thing? Right? Which means that whatever speed you build up to, now I haven't put any numbers on this except for zeros. Whatever speed this is, you're just going to maintain that speed during this next interval, right? Which is going to look, okay, Here's my sort of mistake, is I think I made this too curvy, because ideally, this is supposed to be flush at this point. Okay, so I'm trying to be perfect about it. I got a curve here, like a parabola curve, and then it goes straight line like this. But they should be flush at this point. It should just lead very smoothly and naturally into it, which my picture doesn't quite, but you guys get it should, right? It should lead just smoothly into it. Okay. And what's this car doing during this last second? It's doing what? Hitting the brake. In fact, we did a whole graph just for a car coming to a stop, like a brake, right? If you just focus on that, it was negative acceleration. The car's velocity went to 0. And what did the x versus t curve look like for just the car coming to a brake? Piece of a parabola upside down, right? Did it go kind of like this? Right? So, remember I took you guys over that. Like if you break up the last second, like 2 half seconds, right? Looks like the car was gaining a good amount of distance during like that little segment. And then during the very last half second, it picked up a little bit of distance, but not very much because it was slowed down. Okay. That's why from here to here, it picks up a lot of distance. And then during this last half second, okay, not as much. So it's going to bend down. Yeah, that is a piece of a parabola fix. There you go. That's x versus t. Right? Now, what if I threw you some numbers? Like what if I told you the acceleration values on this car? Do you think you could figure out the change of velocities? And therefore, you can figure out the exact shape of this trapezoid. You guys do see a trapezoid here, right? Can you guys find the area of a trapezoid? There's a formula for it. It's like the average of the bases times the height. Right? Or you could split it up into a couple triangles and a rectangle. Right? And what does the area of that trapezoid represent? This area represents the change in location of the car, delta x. Which, well, if the car started from 0, it would also represent the final location, wouldn't it? Okay. This area represents that change right there. Okay. Okay. So again, if I just gave you the acceleration values and the times and told you that the car started from rest at 0, okay, do you think you could figure out exactly how far the car went? Okay. You know, if I asked that as a quiz question next week, I think you could figure that out, okay. Which you guys do have the solutions for, because this is, again, basically number 20 in your textbook, and I wrote up all the solutions already, so you guys have that. Yeah, you have I should say, an example with some numbers. All right. Okay, that's not too bad. Here. Chapter 3 from your book is a bunch of two-dimensional kinematic questions. Hey, well, we got a bunch of 2D questions. So next week, one of the days I'll take to cover this. I'm looking at Tuesday probably. One day we'll do a lab. And I've got some other stuff lined up. All right, so you guys have a good 3-day weekend.